So in this section, we're going to look at the continuity of a function. Informally, that just means our function doesn't have a break. But formally, this is how we define continuity of a function. We say a function is continuous at a specific number a if the limit as x goes to a of the function is equal to the value of the function evaluated at a, f of a. So this definition implies three things as far as our function is concerned. For it to be continuous, first, it must be defined at a, right? Because we said the limit is equal to f of a, so if f of a did not exist, we couldn't set the limit equal to it. So f of a must be defined, which means a is in the domain. Next, the limit exists, because we said the limit is equal to f of a. That implies from the right and the left, the function goes to the same place as x gets close to a. And finally, that limit and f of a are equal to each other. So wherever the limit goes, the value of the function is in the same place, right? So if I look at this in a graph, here we have a continuous function at a. So if I'm looking at the value of the function at a, the limit from the left and the limit from the right and the limit from the left both go to the same place, and that place is what f of a is, right? So f of a is exactly where the limit would be, right? So basically, again, informally means my graph does not have any breaks. Right, so let's look at a function that does have breaks and does have discontinuities. So here's an example. We have a graph of a function, and we want to know when that function is discontinuous and why. So I think visually we can see that there are a bunch of places when this graph has a break. First one is at -3. So we have a discontinuity at -3 because f of x is undefined at -3, right? So there's no value. That's why there's a hole here, but the function is not defined at all. So if I asked you what f of -3 is, you wouldn't be able to answer it because the function doesn't have any values defined anywhere, right? So next place I can see that the function has a discontinuity is at 1. Right, so when I look at x equals 1, I see that my function has a break in it. Formally, we see that break. We should notice that the limit does not exist, right? So the limit from the left for this function as x goes to 1 would have been 4, but the limit from the right as x goes to 1 would have been 5, right? So the function gets closer to 5 from one side and closer to 4 from the other side. So this function does not have a limit at 1. Therefore, it's not continuous. And visually, we should be able to see that. And finally, the last place that is not continuous is at 2, right? And at 2, it's a slightly different situation that we had at -3. So at -3, the function was just not defined. While here, at 2, the function is defined, right? So if I ask you what f of 2 is, the answer would have been 1. Right, so the function does have a value here, except right there when the graph itself is, the function doesn't have a value. So the limit from the left as x goes to 2 exists. It would be 6. The limit from the right would have been 6, but the value of the function itself is at 1. So at 2, we have a discontinuity because the limit of the function does not match the value the function. Next, we're going to take those discontinuities we saw and actually give them names so we can refer to them as we find discontinuity. So here's another graph, and this graph has 3 places where it's discontinuous. So the first place would be right here where the left limit and the right limit do not match. Then we have a discontinuity here where it looks like our graph would have had an asymptote, and the two ends do not actually touch, and there is a break. And finally, there is a discontinuity here in our graph where the value of the function and the limit of the function does not match, right? So the value of the function all of a sudden is at a slightly different place, right? So again, we refer to these as by specific names. Here, where my limits from the left and right don't match, we call that a jump discontinuity. Our graph jumps from one value to another. The place where we have an asymptotic behavior, we refer to as an infinite discontinuity, right? So our graph is broken up into two parts there because it goes to infinity. And finally, this place where the value of the function doesn't match its limit, we refer to it as a removable discontinuity, right? This one I can remove by, the discontinuity can be removed by defining the function differently, right? So if I take this point and move it up, the discontinuity is removed. Okay, so and sometimes when we have a situation like this where I have a jump discontinuity, we talk about it being continuous from one side. So if you notice, the limit in this case from the left actually matches where the function is defined, but from the right it doesn't. So we refer to those as being either left continuous or right continuous, depending on which limit matches the value of the function, right? So it's right continuous if the limit from the right value matches the value of the function, and it is left continuous if the limit from the left matches the value of the function. So here I have a case where the limit from the right and the value of the function match, while in the bottom one, from the right, the value of the function doesn't match the limit, but from the left it does, right? So the limit from the left would have been 2, and the value of the function is 2, while the limit from the right would have been 3. That doesn't match where the value of the function itself is defined. Okay. So far we've been looking at continuity at a specific point when x goes to a, right? So next we're going to define what it means for a function to be continuous, period. So we say a function is continuous on an interval if it is continuous at every point in that interval, right? And if it ends at the end of an interval, we extend the definition of continuity to be left continuous or right continuous. Okay, so if it's continuous on every point in the interval, we just say it's continuous in that interval. So some properties of functions that are continuous. So if I have two functions, f and g, they're both continuous at a x value a. If I add the two functions, the result will be continuous. If I subtract the two functions, the result is still continuous. If I take the function multiplied by a constant, the result will still be continuous. The product of two continuous functions remains continuous, and the quotient of two functions is continuous as long as the denominator is not equal to 0. Right? So if g of a is not 0, I can divide two continuous functions and the quotient remains continuous. Right? So now that we've kind of talked about what it means for functions to be continuous, we're going to talk about what functions that we are familiar with turn out to be continuous. Right? So our first theorem says that any polynomial is continuous on the entire interval of negative infinity to infinity, right? So polynomials, if you recall, are like 5x cubed plus 7x minus 2, or 20x to the 8th plus 17x to the 4th, and so on, right? So you have coefficients multiplied by powers of x and added and subtracted to other powers of x with coefficients, right? So polynomials are going to be continuous on the entire interval. And a rational function. That's if I take a polynomial, divide it by another polynomial, what we get a rational function. Those are continuous whenever it is defined, right? Whatever its domain is. So basically, whenever its denominator is not 0, right? So a rational function would be defined as long as its denominator is not 0. So its domain excludes the values that make the denominator 0, right? So a rational function would be continuous as long as the denominator is not 0, right? So here's some other functions that we are familiar with, we've seen in the past, and they are continuous on every number in their domain. So if they're undefined, they will be discontinuous. As long as they are defined at a value, the limit will match that value, right? So we already discussed polynomials, rational functions. Here are some other ones, power and root functions, right? So a cube root, square root, they are all continuous on their domain, right? So, for example, square root, we cannot use negative numbers, but for the positive numbers, it would have been continuous. Trig functions, again, sine, cosine, we know their graphs doesn't have, those graphs don't have any breaks. Tangent, it will be continuous on its domain. So not continuous at pi over 2, for example, because tangent of pi over 2 is undefined, but at values where it is defined, pi over 3 or pi over 4, any number between negative pi over 2 and pi over 2, for example, on that interval, it would be continuous. And exponential functions are continuous on their domain. Logarithmic functions are continuous on their domain, right? So a typical log so if I have a natural log of x, I cannot have a negative number, so it won't be continuous for negative numbers, but since I can plug in positive numbers in it, it would be continuous for positive numbers. Okay, so next thing we're going to look at, see how we can take these functions, combine them. So I already know if I add them, subtract these functions we've listed, multiply them together, divide them together as long as the denominator is not 0, we get continuous functions. So next thing we're concerned with is the function composition, right? So what happens if I take one of these functions, plug it into another one, right? So our first theorem says that as long as f is continuous at b and limit of this other function g of x as x goes to a is b, then I can take the limit as x goes to a of f of g of x, and I get f of b, right? So as long as f is continuous, I can evaluate g of x first, the limit of g of x, and then plug that into f, and then evaluate that limit. If I'm taking the limit as x goes to a of f, right? So if I have a function composition, limit as x goes to a of f composed with that function, as long as f is continuous at the limit of g of x, I can first find the limit of g of x and then plug it into f. Okay, so our next theorem says if I have a continuous function g at a and f is continuous at g of a, right? So find g of a, and whatever that value is, f would be continuous there. Then the composition of those functions, f of g of x, is equal to f of g of x, and that is continuous at a, right? So as long as g is continuous and f is continuous at g of a, then the function composition would be continuous at a. Okay, and the last thing we're going to look at here is the intermediate value theorem, right? And the intermediate value theorem says that if f is continuous on a closed interval A to B. So here I have a function and it's continuous from A to B. And we let n be any number between f of a and f of b. So if I pick any number between f of a and f of b, as long as my function is continuous on that interval, so let's just say there's n, as long as f of a and b are not equal, right? Because if they're equal, I couldn't find the value between them, right? And then I can always find the value c in the interval from a to b. So somewhere between a and b, I can find the value c where f of c is equal to n, right? So if I look at this graph, if I find f of c where I have c is equal to n, right? So basically, if my function has no breaks in it, and I look at the values from f of a to f of b, there is some pre-image for those between a and b, right? So any of these values I pick, I can always find a number between a and b, right? That would have them as their image.